Hello everyone, welcome to our webinar on building a low latency voice assistant. My name is Buket and I am a product marketing manager at Telnyx and I am responsible for programmable voice products. Today I am joined by Enzo from our software engineering team and he will be walking you through their journey of developing an advanced voice assistant. Before we start, I would like to say one more thing. At the end of Enzo's presentation, we will have a Q&A session. So if you have any questions, please feel free to share them in the Q&A box. And I think we can start. Enzo, you can take it over.
Sure. Thank you, Bucket. So yeah, as Bucket said, I am part of the software engineer team here at Telnyx. I've been building many features there, and recently we decided to port whatever we can do with LLM into voice. And that's how we started our journey to build a low latency voice assistant. Today in the agenda, we go over the first iteration we've done, then the issue we encountered during our journey, how we fixed some of the issue, one of them being latency, the other one being like the user experience, which was not great. And then we will have like a Q&A session, as Buket said. So for the first iteration, I would like to remind you what we are going to talk about. So for our voice assistant that leverage LLM, we will split that into three different components. The first one being like the speech to text, which is getting the user audio and turning that into text. Then the LLM part, we will leverage LLMs to generate a text response out of the user's text. And then the text to speech, which we call TTS, which generate audio out of the text. I know that today there are other systems that allows you to directly get audio and then get a text output, which basically join the speech to text and the LLM. And we have some model that support that. So if you have any question at the end, I can talk a bit more about that. But yeah. So for the first iteration, at Telnyx, we already have many features that would allow to build such application. We have call transcription, which we can enable to any call, which basically will send you a webhook with the transcription every time the user is done speaking. And then we have a chat completion endpoint, which looks like an OpenAI endpoint, which we can use to actually generate the response. And this endpoint, what is cool about it, it's leverage open source LLMs such as Llama or Mistral. And we have the speak command, which allow anyone to issue a speak command to a call with any text they might want. So with these basic features, what we can do is like the user is speaking, Telnyx will send like a transcription webhook. With the transcription, out of that, we will generate a response. And once we get the response from the LLM, we will issue a speak command with the text. So all of that can be directly built by any Telnyx customer. However, with this, we encountered some issues. And I guess you might have thought about which one I'm talking about. It's very slow. So with our first iteration, doing everything like that, it was super slow. Indeed, like for a voice assistant to be effective, actually in real life, if we speak between each other, the response time between human would be like around 250 milliseconds. And for voice assistant to be good enough, we expect to have a response time between 300 milliseconds and 1 second. And our voice assistant that we built was around like 6 and 10 seconds to get a response, which is very slow. And if you build something like that, your customer won't wait on the phone. They will think something is broken. So we don't want that. The next issue we had was handling interruption correctly. For example, if we take user wanted interruption, so the bot is talking and you would like to interrupt it, it makes it much more difficult with the approach we took. And then, for example, if the user is making a pause in his sentence, everything will be triggered and it will be the bot that will actually interrupt the user, and you don't want that. So first, we will focus on reducing the latency. So remember, we were around like 6 and 10 seconds to get the first audio. So let's see what we've done. The first thing we've done, as you can have imagined before, we were waiting for the full LLM response, which is not very effective because imagine the LLM output like something very big, then your response time depends of the length of the LLM response, and you don't want that. So to overcome that, we leverage like the streaming capability of the LLM, which allow you to get like token by token responses. And what we're doing is buffering this token on our side until there is some kind of punctuation. And we issue a speak command as soon as we have enough buffered token. And with this, you can remove the length of the response of the LLM out of the equation. That way, you only depend of the time to first token of the LLM and the tokens per second. Of course, you need to count like around 10 tokens, let's say, to get like some kind of sentence. But yeah. And with this new improvement, we managed to get down to 3 to 4 seconds time to first audio, which is okay, but not as what we want. So what we decided is to move closer to the media, because what we've been building so far, it's something that any customer could build. But we are in Telnyx, so we could build a system within our system, which would be closer to our media server and directly interacting with media. So we don't have to wait for transcription webhook and all of that. And to do that, here you have a little logo, which is a framework that we use here at Telnyx called Membrane, which will handle the media for us. At Telnyx, we use a language, a programmable language that is not very common called Elixir. And Membrane is one of the framework that allows people to handle media in Elixir. So this is the architecture that we decided to go with. So as you can see, now we have the Telnyx media server that we directly send the user media to our system, to the voice assistant system. And the voice assistant system is going to generate audio and send that back to the media server. However, now we don't have any more transcription, webhook, etc. We need to handle the detection of the end of speech, trigger the transcription, trigger response generation, trigger the TTS, and play the generated audio. So we have to do all of that on our side now. It's a bit more work, but thanks to that, maybe we can build a product that will be much easier for our customer to use, because we do all of that on our side, and that will help them to integrate with us. So the first step was how to detect end of speech. So we took a very naive approach, which was, okay, if there is 800 milliseconds of silence, we will say, okay, the user is done speaking. It's cool, it's a bit naive, but a downside to that, it means that we always have to wait 800 milliseconds to actually do anything. And we didn't want to wait 800 milliseconds to trigger our, let's say, our answer pipeline. So what we decided to do was take this to our advantage. So we decided to also, every time we detect there is 100 milliseconds of silence, to trigger the whole answer pipeline. That way, it gives us like around 700 milliseconds to actually try to build an answer, which is cool. And with that, we managed to get like a time to first audio, which is always more than 800 milliseconds because we have to wait for that. But we get these 700 milliseconds for free, which was cool. Okay, I'm going to talk a bit about Elixir and Membrane for people that are interested. So this is within our system, the voice assistant system that you've seen. Basically, like we will receive our user audio via RTMP on our side, which we will decode, resample, and then we will send audio chunk to a separate gen server. A gen server is a concept in Elixir and Erlang, which is like a separate process, which allows you to scale vertically very easily within your application. And this conversation gen server will spawn another gen server, so another process, which will be responsible only to generate the answer. This is a bit how we've been doing it so far. And with all of these changes, we managed to get to 2.5 to 3 seconds time to first audio, which is great. However, you see like there are still stuff we can improve, like the transcription, the LLM part, and TTS part. So we will start with improving our transcription. So for transcription, first we were using like a Whisper, the base Whisper from OpenAI. And it was giving us like, I don't know if you've seen, it was around 600 milliseconds to get, in average for our use case, let's say, to get our audio transcribed. And we decided to use Distilled Whisper, which is a distilled version of the Whisper model, which claimed to be like 6 times faster than the Whisper. And it performs within 1% error rate, which is great. And this allowed us to get around 250 milliseconds transcription, which is cool. The only issue with Distilled Whisper is that it works great for English. So if you want to have it for another language, you need to have a Distilled Whisper for the different language you want. However, recently, Whisper Large V3 Turbo has been released by OpenAI, which allowed us to have something that is 6 times, or I think it's 8 times faster than the regular Whisper model, but it's multilingual. So we've been experimenting with that. We have it available, but we didn't manage yet to get to the 250 millisecond. We are more around like 800 millisecond for what we are doing. But still, there is a lot of room for improvement that we need to do. So it's still in experimentation. So now we have 250 milliseconds latency for transcription. Now let's move for the LLM response time. So we have a whole squad responsible for that. So for this endpoint that I told you. And basically what we've done is like improve the hardware. And we also improved the framework that we were using. So we started to use VLLM. And for the hardware, we started to use the MI300X from AMD. And with that, we managed to run Yamaha 3.170 billion with a 50 milliseconds time to first token and 40 tokens per second, which was already great for our use case. So we won't go further with that. Also, actually, I forgot to mention something at the beginning. Right now, I'm only showing you like open source solution that we are leveraging, that we run on our system. And this was a decision that we decided to take, like, okay, let's try to have something that run only open source and let's try to make it fast. So that's why you see like we are not using OpenAI or things like that or other provider at the moment. But it's still possible to use them. But it was a choice to use only open source. Okay, so for the text-to-speech API, so we found out that 11 Labs, probably some of you know about this company, do have a WebSocket API, which is very great for text-to-speech. And it works great for when you play with LLM, because LLM returns to you token and you can send token to their WebSocket API and it does the buffering and all of that for you. So we decided to build like a WebSocket API like they do, but the actual engine that will generate audio, we decided to use TTS2, which is an open source software that an open source model that allows us to get to a decent time time to generate audio. The only downside is that it only English for now, but it was good for our use case. And yeah, for if I can say more about the text-to-speech area regarding open source, it's a bit lacking behind when it comes to open source compared to the speech-to-text or the LLM part. But I think it's going to improve in the following years. Now we've managed to reduce our latency. So as you can see, to 1 second with all of these changes, we will see like how we can improve the user experience. Okay, so first we decided to change a bit the way we were detecting end of speech. At first, we were waiting for this 800 milliseconds. So it means like we will never be able to go below 800 milliseconds to answer something. So we wanted to change that. And something else was if a user makes a pause of 800 milliseconds, let's say, and then resume speaking, then we will kind of interrupt him in the middle, and we didn't like that. So we were like, okay, maybe if human can detect when their speaker is done speaking, maybe we can have a model to do that as well. So we tried to build our model and we open source it. And the model takes like 700 milliseconds of audio input or even less. And with 10 milliseconds inference, it tells you if it's end of speech or not. Of course, it can be improved and it's still the beginning. But that was our goal, like being able to detect end of speech and not have to do what I showed you to wait 800 milliseconds or have this 100 millisecond window, which make the code a bit complex. So this has been developed by one of my colleagues, Stefan Petrovsky, and it's open source, so you can check it if you want. One thing that we learned from that is that it has a lot of issues. It has a lot of errors. The errors can be separated into two different ones, the false negatives of the end of speech model and the false positives. So the false negatives means that we don't detect end of speech when it should have. And what we've done is that we have put 800 milliseconds of silence guard like we had before. And if this happened, then we say, okay, it's an end of speech and we just missed it. But this increased the response time by 800 milliseconds every time this happens. And the other one were the false positive. So it means like we don't detect end of speech when it shouldn't have. Sorry, it does detect end of speech when it shouldn't have. And what we've done for that is to, for example, if we say like, okay, it's an end of speech, so we start to process the response and then you speak again, we are going to delete whatever we were doing and start again. So we have this capability to say like, if the user speak again, we can erase what we were doing and start a new process. So this allows us to handle the false positive as well. And what is very cool about that is that we can detect false negatives and false positive, which allow us to keep training our model, because now we can easily label like every chunk of audio that were actually end of speech or not, and we can just retrain our model. So we can iterate on that, which is great. Now, the other thing that was hard to deal with was the noise. So imagine like you are spinning up a voice assistant and the voice assistant is speaking, but you have noise in your background. You might interrupt the bot and you don't want that. So to handle the noise, we decided to use zero voice activity detection. instead of just using like the basic silence that we were doing, which allowed us to have something way more accurate than the basic math, which was calculating the power of the signal that we were doing. And we also started to use errant noise to actually suppress any noise from the incoming audio. And this is an area that we will keep iterating because we think it's very important to have as little noise as possible to have a good functioning voice assistant. And yeah. So I guess, yeah, okay. So it's the end of the presentation more or less, but we have some demo for you. So to tell you a bit about what you see here on the screen, we told you about this voice assistant, and recently we productized it into our offering. And one way we found to productize our assistant was to build a gather using AI command. So for those familiar in telephony, usually like most of the gathering can be done in two ways. Either you collect DTMF from your user. So it means like people are pressing digits on their phone and we can tell you which digits they have pressed. So it works great for example, if you want to get the zip code of someone or things like that. Or it can be done by doing like playing some audio and then doing some transcription and all of that. So here we decided to build like a gather command where you can see here the parameters just says like there is a greeting that says like that would be the first thing the bot will say. And then you have some parameter which are actually the parameter you want to extract from the user. So here in this example, it's the age and the location. And so this will be part of the call control command body. And on the right, you can see like what you receive as a webhook. So let me show you a demo and try to pay attention to how fast the bot will answer my question, etc. So let's try.
Hello, can you tell me where you live?
Hello, I live in Paris.
Could you also tell me your age, please?
I am 29 years old.
Okay, so as you can see, like the bot was supposed to get the age and the location. And first I said like, okay, I live in Paris. And then it follow up asking for my age. So, and you can see the result comes in a format that you expect because this is what you provide in the properties. So age as an integer and location as a string. So this is one way to productize what we've done. And then I have a second demo, which is using a new tool called Flow that we've built, which basically, I mean, right now what I showed you was you need to issue a call control command. So you need to have some server-side logic to issue API commands to Telnyx. And in this tool Flow, it does it basically for you. Like you can draw some flow, so some call flow, and you will say like, okay, issue a gather command and then do this, etc. So you will see all of that in the video that I will show you now. So this is a short demo to show you how we can use Flow to build like some sort of voice assistant that also rely on gather using AI command behind the scene. So let me show you. We can use like JSON files, which defines a flow and that can be shared between people. So here I have a US weather bot that I'm going to configure. You see like it has multiple nodes, etc. So first thing I need to configure is to assign a voice application. So I'm going to use this one that I've prepared for this demo. And then I just need to make sure like single API key, and we should be good. Okay, so this flow in theory combine multiple nodes in order to build a weather bot. So it will first answer my call, speak some texts, then it's going to ask me like which city I would like the weather for. Then it's going to extract the result of the gather command and make requests to another endpoint that will allow me to get some forecast. And then it will use like a node that will execute the chat completion endpoint to build like a proper text out of this result. It's going to give me the result. Then it's going to ask me like if I would like to get another city using gather using AI. And then if I say yes, it will jump again to the first node and so on. So let's try.
I'm Nix, your friendly weather assistant. Which US city would you like the weather forecast for?
For Chicago, please.
Okay, I'm looking up the weather forecast for Chicago now. The weather forecast includes mostly cloudy conditions with scattered rain and snow showers, windy conditions, and temperatures ranging from 15 degrees Fahrenheit to 49 degrees Fahrenheit over the next few days. Would you like to ask about another US city?
Yes, for San Francisco, please.
Which US city would you like the weather forecast for?
For San Francisco, please.
Okay, I'm looking up the weather forecast for San Francisco now. The weather forecast predicts mostly clear and sunny conditions with temperatures ranging from the high 40s at night to the mid 60s during the day. Would you like to ask about another US city?
No, thank you.
Okay, have a great day.
All right, and you can see like the flow executed twice because I asked for 2 US city, and there you can see everything I said in the different node results, and that's it. So this is a short demo to show you. Okay, so to wrap up this webinar, I mean what I presented. Some key components. So we use Membrane and Elixir. So we use Elixir a lot in our company, which make it super easy to scale application, etc. It's not very known, but we hope it's going to be known more in the future. We've been using Elixir since 7 years at least at Telnyx. The latency is very key for any voice assistant. Otherwise, like the customer will not engage, let's say. Interruption as well is very important. And then one thing we learned was to embrace false positive and negatives, as we've seen for the end of speech model. And last but not least, like iteration. We use, I mean, probably a lot of you do that as well, like start small and then iterate, measure and repeat, and until you get the result you want. So this is how we get through our journey.
Now it's time for questions. And so we have many questions. Let me ask you the first one. What is the average time for the first audio to first audio?
Okay, so it depends of multiple factors. It depends of the LLM being used, the transcription, etc. The best we managed to get was between 800 milliseconds and 1 second. This is what we managed to get, but it highly depends of the text-to-speech engine and the LLM, I would say. But at Telnyx, like for what I showed you, like the gather command, you can specify different LLM, you can specify different text-to-speech, I mean, different voice provider. And yeah, you can play around that.
Let me skip to another one. Can you speak about 11 Labs integration issues?
So if you want to use, so that's true, we can use 11 Labs. The only downside right now when you use 11 Labs is like you need to make sure that you are using an account that is you have multiple tiers in 11 Labs, and you need to use an account that has a sufficient tier. Otherwise, 11 Labs see the request coming from us, and they think like we are using multiple free accounts, you know, from the same IP, and we get issues.
Okay. There is another question about, is any work being done to make it sound more natural?
Sure. So basically, like this depends of the text-to-speech engine we are using. So as I mentioned, like we can use 11 Labs, which sounds more natural. There is also we integrated recently with AWS, neural voices, which make it sound also more natural. So it depends, like, but again, like you need to play with the balance of latency, right? You need to play around. So try one voice. If it's good enough, go with it and check the latency. Yeah.
I want to use my other speech to text provider at my end. I can do that using the media stream, right?
That's a good question. So we have this media streaming API that we provide to our customer, where we basically give to you the voice via WebSocket, and then it's up to you to do like a transcription, then send it to the LLM, then you have the audio, and then you can use your your STT provider. So yeah, for speech to text, as soon as you get the audio, you can use your STT provider, but then you will need the LLM. And once you have the LLM, use like some text to speech provider, or you can use the speak command. So everything that the LLM returns to you can be sent in the speak command.
Okay. I think we covered most of the questions, but I am checking again. And so also if you want to add anything else, please go on.
Yeah, I see, like, can we change voices, English? Okay. The one regarding voices, there are two things that are important. First one, what I've presented to you works great in English because our transcription mechanism is in English, and you can select any voice that works in English. And yes, you can have, if I'm not wrong, on AWS voices, you can have English US, English UK, male, female, etc. However, if you want to go multilingual, you will need to use, like, there is a parameter you can use to select a different transcription engine. However, right now, I feel it's a bit slow. We are improving it, which will allow you to use also like a multilingual voice, which right now we only have 11 labs that supports it to have multilingual, and that would provide you a way to build an application that is multilingual. And regarding the question that says like, how do you move something like you demonstrated in Flow to a live running assistant via phone? This is a good question. So in the example I showed you, you see like I'm clicking a button to actually trigger the phone call. However, what happening, it leverage like our voice SDK to make a phone call to a number. But in the end, like if you just call the number from your phone, that would be the same idea. So do you have any customer using this? Yeah, we do have a customer using this production, this scenario in production at the moment, especially like the gather using AI that I showed you. Flow is just a different flavor.
Let's take last two questions and then we can answer all of them also offline. So
I see like a question around like gather lives in Flow. So Flow is just a way for customer to play with Telnyx command without having to do any code. So gather is being made out of flow. Flow is just a way for people to not have to code anything. But gather is a logic that is outside of flow. Flow is just making requests to Telnyx API at the end, but everything internally. So you can gain, you can gain into some latency. And I have a question that I see that says like, I'm wondering how it scales. So right now, what we built scales very well. I mean, all the components that I showed you are scaling very well. Yeah, I mean, we've built that with this in mind, and we didn't find any issues on our load test. And Telnyx, I mean, probably you guys know all of that, but we use Kubernetes, and basically like we have auto scaling for almost everything. So yeah.
Yeah, I think we are running out of time. So last question maybe we can get, and then
Let me check. The model, I see this question 2 times around like if a model is open source. I assume you guys are talking about the end of speech model. Yes, it's open source and you can use it in any of your project. If you are talking about this one. The other one, we are just, the other open source thing I've talked about are made by other people and they are open source, so you can use them.
yeah. I think we covered most of the questions, but if there are any other topics or if you have more questions, please write them in the Q&A box, so we will get back to you later on. And also, if you want us to cover those topics in our upcoming webinars, please let us know and write them to the Q&A box again. So I think for the day, that's it from us. Thank you, Enzo, for your detailed presentation and demo. And thank you for everyone who joined us today. You can receive all this recording and the presentation. So, and also we have at the end of the presentation, we have also other related links for your further explorations. So thank you so much and have a nice day.